All right, chapter 1, matter, measurement, and problem solving. We've got a quote from Albert Einstein: the most incomprehensible thing about the universe is that it is comprehensible. The craziest thing about the universe is that we can understand it. What do you think is the most important idea in all of human knowledge? If we were to limit ourselves to science, particularly to chemistry and maybe some physics, it might be that the properties of matter are determined by the properties of molecules and atoms. Atoms and molecules, the tiny little building blocks that make up the world that we inhabit, that we enjoy, hopefully, determine the properties of the world that we inhabit. And so part of the joy of chemistry, one of the cool things about chemistry, is that by learning how the tiny little building blocks operate, learning how those operate can tell us more about the world that we inhabit, the world that we occupy. It can provide some explanation for why our world is the way it is. So atoms and molecules determine how matter behaves. If they were different, the matter would also be different. And so that's pretty cool. Atoms are the submicroscopic particles. They are very small, unfathomably small, I usually say. These are the particles that make up the building blocks of ordinary matter. So anything that's on our periodic table in class or anywhere else, any one piece of those elements is an atom. The smallest piece of an element is an atom. And you can link those atoms together. They're usually not free atoms where it's just one atom by itself. Usually they link together in things like molecules. So molecules would be certain types of atoms fused together, linked together to form a group. And water is an example of a molecule where we've got an oxygen atom represented here by the red sphere overlapping with two hydrogen atoms represented by the white spheres. The properties of the water molecule, an individual one piece of water, determine the properties of water. And so the water molecule, as we know it exists, is H2O, we would call it. There's two hydrogens, there's one oxygen. If we changed it just very slightly, if we add another oxygen in there, then it becomes hydrogen peroxide, which is good for cleaning things, not great for existing. It's pretty bad for you if you were to consume too much of it, but great if you want to whiten your teeth. There's other ways that we could change water. For example, if we changed the shape, it does have this bent shape where the hydrogens are kind of sticking down at angles or up at angles depending on how you rotate it. If we were to theorize about the shape of a water molecule, we might think that the hydrogens are sticking straight out to the sides in a linear pattern. If water was linear, we wouldn't exist. It would be a completely different world. So just things like the shape of the water molecule make our existence possible. So in chemistry, our goal is to understand the behavior of matter, big things that we can experience, things that we can see and perceive and touch and smell, by studying the behavior of atoms and molecules, which we can detect with expensive instrumentation, and we know are there because people have told us so. So for example, the difference between graphite and diamond: graphite is all carbon, diamond is all carbon. The way that the carbon molecules are connected to each other is the difference between diamond and graphite. One's very expensive, artificially so, and the other one is far less expensive. We use it in our pencils. One of the ways that we come across or come about some of this knowledge is through the scientific method or the scientific approach. You've hopefully encountered the scientific method before. You should have talked about it early on in Chem 20 or high school chemistry. You should have also maybe talked about it in elementary school. I think that's when I learned it. So the scientific method is a process that we can use to try to understand things. I don't know that I've ever talked to anyone who talked about their research like, oh yeah, we used the scientific method and we did this, 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 and this. It's sort of just like a general guiding philosophy more than it is a hard and rigid set of processes. So there's some key characteristics. We'll talk about each of them. Observations. so things that you can observe, also known as data, the plural of datum. That's just for fun. That's free. So datum is one point of data. I don't know why it's that way. It's just the way it is. So for example, with some observations, Antoine Lavoisier, French, made some measurements about the mass of objects before he put them into this contraption and after he burned them in the contraption, the closed container. He noticed that there was no change in the total mass of material within the container during combustion. So throw stuff into his glass jar thing, light it on fire, seal it up, let it burn, and then afterwards the mass is the same. So despite the complete rearrangement, despite it looking totally different, things going away, same mass inside. And so based on those observations that he made, that led to the formation of a hypothesis. A hypothesis, I believe the way I learned it, was an educated guess. A tentative explanation, something, a theory, but theory is what we would call something else. That's a different thing later, but we might call it a theory. So it's an educated guess about why those observations were the way that they are, something about them. Lavoisier explained his observations of combustion by hypothesizing when a substance burns, it combines with a component of air. We probably all know this. Most of us know this. If you're burning a candle, you can just put the lid on and it goes out. Or you've got the little fancy like bell-shaped thing that you can stick over your candles if you're really fancy. Or if you just like to have fun. I feel like that's fun. A good hypothesis is falsifiable. It can be proven wrong. Or false. If your hypothesis can't be proven false, it's not helpful. For example, if I have a dog, but let's say that I leave some food out on the countertop where the dog could not possibly reach it, and in the morning I wake up and the food's gone, the snacks are gone, the chips, the whatever it is gone. If my hypothesis is that an invisible, untraceable man has entered my house silently through the walls and eaten my snacks and chips and left, how could I prove that? I could not possibly prove that an invisible man did not do those things. That's not a very good hypothesis. A better hypothesis would be something related to maybe my dog just can get places that I didn't expect, or maybe I've got mice or rats in the house, which would be horrifying. They're in the garage, but in the house, too far. So I could set up, a camera to watch it. That wouldn't catch the invisible, unseeable, unknowable man. However, it would catch my very visible dog and or other animals. So that would be a much better hypothesis. Following up on hypotheses, our educated guess, we would want to design some experiments. Our experiments ideally are highly controlled, especially in a science setting. There's oftentimes a lot of variables. Things like temperature, time, amount, type of thing that we're using. And we would like to control as many of them as we can, keep them the same, and then test one variable at a time, change one thing and see, does that fix the problem? No, it didn't fix the problem. Test another thing. Did that fix the problem? No, it didn't fix the problem. Test another thing. I did that with my rat's nest of cables today. I unplugged all of the cables and I plugged them back in one at a time. Was this the problem? No, it wasn't the problem. Turns out it was in the software. So I just deleted the capture source and then attached it again, and magic, it works. So problem solving often similar to our scientific method. The result of our experiment may support a hypothesis or prove it wrong. That's why we want a falsifiable hypothesis. And then we can modify, make some changes to our hypothesis, our guess, or we can just completely throw it out and start anew, depending on how the results work out. From the results of our experiment, we might come up with a scientific law. And a law states what happens. It summarizes past observations and it can predict future ones. if A happens, then B will happen. Whatever A and B happen to be, but it would be something of that form. So if I drop food on the floor and say, oops, then my dog will come running. He's learned that oops means there's food on the ground. So that might be a law. The theory, which we'll get to, is that he understands what oops means. So the law of conservation of mass came sort of out of Lavoisier's experiments and observations. It states that in a chemical reaction, matter is neither created nor destroyed. So combustion, burning things, is a chemical reaction, as we'll talk more about later. And when that occurs, matter is neither created nor destroyed. So the amount that we started with is the amount that we will end with. If we burn something and we capture all of the things that burned, including the smoke and the other invisible particles, if we capture those, then afterwards we should have the same mass. Scientific laws are also subject to experiment. They can be supported by these experiments. They can also be proven wrong. So occasionally we throw out scientific laws. Unlike state laws, scientific laws can be violated. I mean, you can violate state laws and federal laws too. It's just there's consequences if you get caught. So scientific laws just describe how nature behaves. Usually there's some way around them. Not always, but sometimes. Theories are the other thing that we can arrive at out of observation, hypotheses, experiments. So a scientific theory is why something happens, or it can be used to explain why something happens. So rather than just saying, if A happens, right, if I drop food, then my dog will come running. I drop food, I say oops, the dog will come running. The theory is if I say oops, my dog will come running, he knows that oops means there's food on the floor. Something to that effect. It's a much better analogy than I used yesterday, which is all about the bathroom. Ask me later. And so an example of a theory related to the law of conservation of matter, John Dalton's atomic theory. John Dalton came a little bit later to this planet than Antoine Lavoisier. His atomic theory explained the law of conservation by proposing matter is composed of small, indestructible particles called atoms. That's the atomic theory, part of the atomic theory at least. So since when we're doing combustion or chemical reaction, since they're made of small particles that can't be broken, can't be destroyed, only rearranged, when we rearrange them, we should have all the same amount of particles. This would be kind of like if you had a really cool thing that you made, like out of a Lego set, and then somebody or an animal came along and crushed it, assuming they didn't eat one of the pieces or destroy one of the pieces completely, somehow magically, you could reassemble the Lego set, assuming that you have the instructions, or you're just that good, you're built different. So that's sort of the same idea. Chemical reactions are kind of reassembling a Lego set or rearranging the pieces of a Lego set. Theories can also be validated by experiments. You can't really conclusively prove a theory because it's always possible that there's some flaw, but usually they get kind of more and more ingrained in our, like, yes, this is always true, in our scientific teaching. Theories can provide good general explanation for characteristics and behavior of nature. They can also be used to predict future observations. So this is part of why theories are better than laws. Laws kind of just one thing applies to another thing. Theories, we can extrapolate that idea to apply to other things as well. So maybe I don't even drop food on the floor and I just say oops and my dog comes running in. Again, because he's learned that oops means there's food on the ground, even if he didn't hear it fall. Here's an example of kind of the choose your own adventure of the scientific approach, the scientific method, starting from observations, sort of measurement or description of a characteristic. You can go straight to laws if you get a lot of observations. Generally, you're going to develop a hypothesis, and that will lead to experiments or maybe to a theory. and then more experiments, more testing to confirm or revise our hypotheses, our laws, our theories, etc. Questions about the scientific method or atoms and molecules? Cool. Which of these statements best explains the difference between a law and a theory? Think about it. Any guesses? A, B, or C? B. B, a law summarizes a series of related observations. A theory gives the underlying reasons for them. That's correct. C looks like it could be correct. It says a theory describes what nature does, a law describes why nature does it. These two are flipped. They're in the wrong spot. Law and theory would be swapped, and then it'd be correct. A law is truth, a theory is mere speculation. They're both not entirely truth. It's just we know that some things happen. All right, moving on to matter. Matter, we've talked about a little bit. Matter is anything that occupies space and has mass. So your book, the tables, the desks, the chairs, the people occupy space and have mass, so they are matter. A specific piece of matter we might call a substance, or a specific type of matter we might call a substance. We can classify matter according to its state, physical state, solid, liquid, gas, etc. And also its composition. What is it made of? Is it one thing? Is it two things? What type of one thing is it? What type of two things is it? And we'll talk about each of those. So the states of matter, hopefully already familiar to you, but we'll cover them briefly. Matter in this class we'll classify as either solid, liquid, or gas based on some of the properties, how the little pieces are arranged relative to each other. The state of matter can change from solid to liquid to gas with increasing temperature. In terms of temperature, our lowest temperature state is going to be our solid. Above that, liquid. Above that, gas. Not everything in all environments is going to have all three of those, but you should have at least two. So talking about our lowest energy state of matter, relatively, solid matter, our atoms and molecules are packed close to each other, as I describe it, touchingly close. They can interact with their neighbors, and they are in fixed locations. So as close as they can possibly get, usually, or very close to it, and they are also locked into their positions. So the atoms and molecules in a solid will vibrate. They move in place. They're not going to move around or past each other. It's sort of similar to all of you sitting here in the lecture room. You're all, mostly, sitting in a seat, staying in one spot, and you're moving around. You're still living, you're breathing, you're writing things. So you kind of imitate or mirror a solid state. You're not switching seats with your neighbors. Another example that I like for a solid state is people at a movie theater. Everyone's in their seat, they're eating their popcorn, they're drinking their snacks, etc. They're doing whatever they're doing, but they're not switching spots with their neighbors. And they're all kind of packed in as close as they can be, assuming that it's a good movie or it's, just a lot of people are there for some reason. Some examples of solids: ice, which is solid water, aluminum metal, and diamond. Solids can be crystalline. Crystalline means that they have long-range repeating order. So if you were to zoom in and look at like the atomic level, and you took a snapshot and then you scrolled over, if you scanned over a little bit, you'd be able to get those two images to overlap perfectly because it's repeating the same order. Things like quartz are crystals. So part of the reason that they have the shape that they do is because of that long-range repeating order. It extends to such a great order that we can see the way that it repeats. So different crystals will have different shapes that they'll form, different facets that they like to take on when they form naturally in nature. And that's because of this long-range repeating order extending out to unfathomably large numbers of units. So things like table salt, which if you get them big enough are big crunchy crystals, diamonds. Other solids are amorphous, where the atoms or molecules have no long-range order. So it's more of a random arrangement compared to our long-range repeating order. Quartz is actually, depending on the type of glass, the same chemical composition as glass, but quartz has regular long-range repeating order. Glass is amorphous. So they have slightly different properties. You may have heard falsely that glass is just a really viscous liquid. It's not true. There's lots of reasons for why it's not true, but it's definitely a solid. It's just amorphous. So if you were to zoom in at that atomic molecular level and then scroll over, you wouldn't be able to get those images to overlap in most cases. In our next highest energy level of matter, we've got liquid. In liquid, our atoms or molecules are packed about as closely as in solid matter, still touchingly close. They're interacting with their neighbors. However, they've got a little bit more energy, and so they can move. They're free to move relative to each other. So because they're touchingly close, they're packed in about as tight as they can get. They have fixed volume, but since they can move past their neighbor, they don't have fixed shape, and that's the reason that liquids can flow. Things like water, gasoline, alcohol, not in that order, are all liquids. The reason that hydraulic presses are so powerful is because liquids can flow, but they're not compressible, which I think is really cool. So you can apply an amount of pressure over a very large surface area and then funnel all of that pressure down into a small area, and it amplifies that pressure. It condenses all of that pressure, and that's how you get the extreme power of a hydraulic press. Liquid matter, the analogy that I like to use is like people at a concert. Usually they're all packed in up in the front, depending on the type of concert. That's not going to happen at like the symphony or whatever. But they'll all pack up to the front, and everyone's as close as they can possibly be, but you can still move past each other. If you and your friend are next to each other in the front, you can maybe swap places because you want to talk to somebody. Or if you need to go use the restroom, you can work your way out of the crowd and then try to work your way back into the crowd later. So you're able to move past each other. You are still touchingly close. In gaseous matter, they're not touchingly close. There's empty space. So empty space between particles, atoms, molecules, etc. And because of that empty space, you can compress gases. They're also free to move relative to each other since they're not touching their neighbors. So because of that empty space, you can push on a gas and it will compress. You're just removing some of that empty space. You're forcing the atoms, the molecules, to be closer to each other. So this is the reason that once you finish drinking your $1 plastic water bottle, you can twist it up, it compresses, and then you can shoot the cap off into the air or into your friend, wherever you decide. That's the reason that you can do that, because gases are compressible. So things like helium, nitrogen, which we're all bathing in nitrogen practically, and carbon dioxide are all examples of gases. And gases is sort of how you all behave when you leave class. You're kind of in a solid state right now. Once you get up and you're going to leave, sort of more of a liquid state, and then you go and disperse, and you go your separate ways, and you're, mostly not touching, and there's lots of empty space between you. So that's classifying matter based on its state, based on its solid, liquid, or gas. We can also classify it according to what are the pieces of the matter. So what are the smallest little bits? First, we would have to say, is it matter? Is it a variable composition? So can we change the amount of one thing relative to another? Do we have multiple things in there? If yes, then we would be in a mixture. If it's not, if it's just one thing, then it would be a pure substance. And we could separate out further from there. So our first division, our first split in our classification, we've got pure substances, just one thing. At our smallest unit, our smallest piece, if we count up all of them and we check them, they're all just one thing, or at least mostly one thing. So it would be all water molecules, it would be all nitrogen molecules, it would be all sulfur atoms, something like that. A mixture, on the other hand, is two or more things combined. Lots of things are mixtures. So if we've got two or more components mixed together, that would be a mixture. So mixtures are mixed, multiple things in them. It's not just one thing. Our pure substances we can further subcategorize into elements and compounds. Our elements on the periodic table. So if it's something that's on the periodic table and just that thing, then it would be an element. If we can't break it down any further, that would be another way that we might classify an element. Compounds would be multiple elements together. So like H2O would be an example of a compound. Water is a compound. For elements, iron, copper, maybe depending on how you classify it, nitrogen gas, I'd say it's an element. Yeah?
So like would a diamond, for instance, be like an element or compound? It's just carbon?
It's just carbon. I would probably classify it in element. All right, so elements, things that can't be chemically broken down into simpler substances. Oh, here, composed of a single type of atom, like helium, so regardless of how many. That's how I would think of it, at least. Helium does exist as just He, individual atoms. All of our noble gases in the far right column would do that. Our compounds are two or more elements in fixed, definite proportions. So the subscripts that we see after the chemicals symbols, those are those fixed, definite proportions that make something a compound. A lot of our elements are chemically reactive. They don't like to be by themselves, and so they'll combine with something else to form compounds. Or they're forced to do that by bacteria, us, other things that live. For our mixtures, we can categorize them two ways: heterogeneous and homogeneous. So they're both geneous, one's hetero, one's homo. The categorization depends on how uniformly or smoothly the substances within them will mix. So heterogeneous mixtures have varying composition. Different ratio or composition throughout. The hetero prefix meaning other or different, something along those lines. And usually you can tell. So for example, if you were to mix salt and sand together, that would be a mixture. You would be able to tell the salt versus the sand, assuming it's not white sand, because they have different looks. The sand would be whatever color the sand is, and the salt would be usually white, unless you're fancy. Other examples of heterogeneous mixtures: oil and water, like in a vinaigrette salad dressing. You have to shake them up before you use them because they separate out almost right away. So you shake them up right before you use them, and then you get both oil and water and all the other good stuff that's dissolved into one or both of those in your salad, instead of just a bunch of oil. That can be a salad dressing in and of itself, but usually not what we want. And then a homogeneous mixture is multiple substances, but they're smoothly combined. So the geneous part sort of being like the consistency, and the homo being same. So same consistency throughout. Another way that you could think of heterogeneous versus homogeneous: in a heterogeneous mixture, if you were to sample from any two spots or any multiple number of spots, you would get different ratios of the things that are in there. Or you might get completely, like in the vinaigrette or oil and water, you might get just water sometimes, you might get just oil sometimes. That would be a heterogeneous mixture. In a homogeneous mixture, no matter where you sample from, it should be roughly the same. So for example, sweetened tea or lots of sodas and other drinks like Pepsi, Dr. Pepper, Coca-Cola, you would probably be horrified if you took a sip from your Pepsi and it tasted different, and then you took another sip and it tasted different from the first sip. That would probably be unsettling. Or like you put your straw into a drink that doesn't have ice in it, and you drink from the bottom and it's got a certain flavor, and then you pull the straw up a little bit and you take another sip and it's got a different flavor. That would probably be unsettling to most of us, I would imagine, because we expect our sodas, our drinks, to generally be homogeneous mixtures. And the reason that they have that uniform composition is because the atoms and molecules mix uniformly. So they play nicely with each other. All right, and then to test our comprehension on substances and mixtures, take a look at these three images. A blue circle represents a type of atom of one type of element. A red square represents an atom of a different type of element. Which of these is a pure substance? Any guessers in the chat? We've got guesses for A. A is the correct answer. So A is our pure substance. The type of pure substance that we have is a compound. So we've got red and blue, square and circle, grouped together, and we only have square and circle units. In B and C, the red and blue are not connected. So we've got separate red and blue. That makes it a mixture. So both B and C are mixtures. B is somewhat evenly distributed. It's like well mixed, we might think of it. So this I would call a homogeneous mixture, or it's more close to a homogeneous mixture. And C, they've completely separated out. That would be a heterogeneous mixture. Questions about pure substances, elements, compounds, mixtures, heterogeneous, homogeneous. All right. We'll talk briefly about separating mixtures. So mixtures can be separated because different components typically have different physical or chemical properties. Sometimes they're similar enough that we can't separate them. Oftentimes they're not so similar that we can't separate them. So we can separate them, is what I'm trying to say. There's a bunch of techniques that we use. One of them that we'll probably end up using in this class is decanting. So if you're trying to separate a mixture of sand and water, you can separate that by decanting. Decanting is just pouring off liquid. Sometimes we might separate by decanting by just trying to pour off the top layer of two liquids. Usually we're just trying to pour out liquid. So if you have experience washing rice and you don't use like a strainer that's made specifically for washing rice, you put your rice in a bowl, you put water in, you stir it around, and then you pour off the water and you try to keep all the rice in there. That's decanting. So many of you have maybe done decanting before. If you haven't done decanting and you've made rice, make sure you wash your rice. Not all types of rice, of course, need to be washed. Another way that we can separate mixtures is by distillation. So if you've got a homogeneous mixture, we can distill it. This is the same kind of distillation that like people would have been doing during the Prohibition. So in distillation, a mixture is heated and we try to boil off or evaporate the more volatile liquid. That volatile liquid we would then try to recondense because we want to separate them, we don't want to just get rid of it. So we try to recondense it somewhere else down the line. An example of a distillation setup might look like this. We've got our mixture in a round bottom flask with an extraordinarily long arm, or maybe I'm just missing the joint. We heat up this mixture. The more volatile liquid is going to boil at a lower temperature. Usually you'd have a thermometer coming in the top to check your temperature. And then because the top is sealed, it's forcing the air, forcing the whatever is coming out of this mixture down through this condensing tube. The condensing tube has a hollow tube on the inside that the gas can flow through, and then a water jacket on the outside where water can flow. So we put cold water in from the bottom, and that cold water comes out from the top. And this cold space gives that volatile liquid something where it can run into it, lose all of its energy, and turn back into a liquid and condense. And then it comes down and collects in this round bottom flask in this case as hopefully a pure liquid. Sometimes you might have to go through multiple steps in order for distillation to be successful. This is the typical technique, I think, for coming up with essential oils. If you have the glassware, you can do it at home. It's relatively safe. Another way that we can separate mixtures is by filtration. So a mixture is poured through filter paper or something that's like filter paper. Filter catches the solid. So pour over coffee sort of uses a similar concept to this, except that you're pouring the water in over the grounds that are already there. The filter paper is there to keep your coffee grounds from going into your coffee, because it's not particularly nice to have chunks of coffee in your coffee. I like my coffee to be homogeneous. Usually in filtration, you'll have a mixture of things, and you pour them into a filter or into a funnel. They're not always conical. Sometimes they're flat at the bottom. Buchner and Hirsch funnels being examples of those. But the filter paper hopefully catches all of the solids, and then the liquid component can go through. Sometimes you might have to go through multiple rounds of filtration, depending on how fine your particles are. Any questions about separation techniques? Great, then we will wrap there for today.